Okay, hello everybody. Welcome to the XAS tutorial. So let's start. Again, welcome everybody. My name is Kirill Lomachenko. I'm a beamline scientist at ESRF at BM23 and ID24 beamlines, the XAS beamlines. And this morning I'm going to talk about the X-ray absorption spectroscopy. This is going to be a very introductory talk to give a flavor of what it is and why you might need it. And it's basically oriented to those who have none or very little experience with XAS. So it's going to be like a very basic introductory talk. And the contents is as follows. We're going to talk about I'll present the technique in general. We'll talk about the XANES and EXAFS parts of the big XAS family of techniques, and I'll discuss a little bit the experimental part of XAS, and I will present some of the XAS facilities in the ESRF. Well, some because there are quite many, so I'll focus on those where I work and what I know best. So, starting the introduction. You all know that the structure of materials defines their properties. So the materials that have basically the same composition, like coal, graphite, diamond, graphene, they have very, very different properties. And that means that, well, structure defines the properties. And in order to understand the properties, we need to study the structure. So when you work on some new material, you synthesize it, you want to understand how it works and why it works in such a way, you start having particular chemical questions about the coordination numbers, bond distances, oxidation states, the symmetry, and all this may help you to understand why your material works in one way and not in the other. But you don't want the answer to these questions just for some very particular test case when your material is, I don't know, at 0 K in vacuum. No, you want this, and if it's not even your material, but some imitation of your material that suits best your technique. No, you want the answer to these questions for real world samples, so your actual catalyst or battery or whatever you're studying. You need the answers very often in situ and operando. So when your material is actually doing the job, when your catalyst is catalyzing a reaction, when the battery is charging, so on, you need it with a time resolution that is characteristic to a process that you are studying. And sometimes, actually quite often, you want to be element selective because only particular chemical elements that are present in your materials, particular chemical species, define the properties of your material, properties of interest. Like, for example, it can be the active sites of your catalyst. And XAS, X-ray absorption spectroscopy, it is a technique that can give answers to at least some of these questions under at least some of these constraints. And well, sometimes can satisfy them all, sometimes not, but in principle, it's something that can be done with XAS. So the principle of the method is very simple, and it's to illustrate it with, it's probably best with a simple optical analogy. So when you shine a white light to a filter, let's say a green filter, while you've got a green passing through. Why? Well, because you have a very low absorption in green and a high absorption in red and blue. And this dependence of how much you absorb light on the energy of the light. It's basically an absorption spectrum. And X-ray absorption spectrum, it is the same idea, the same thing, but in the X-ray region. So we don't have colors, but we still have different energies of X-ray photons. So if you take a material, a sample, absorber, in the thickness X, and you shine light on it, X-ray light on it, of particular energy, if you have an I0 intensity before the sample, then some radiation, some part of the radiation will be absorbed in the sample. You'll have I1 density after the sample. The relation between I0x and I1 is given by this expression, a Lambert-Beer law, where I0, I1, and mu are functions of energy. And mu is the thing that we are actually looking after. It is called X-ray absorption coefficient. And just from this formula, you can see that we can measure it. And it's quite well. I mean, it's pretty easy thing to do on in principle. In practice, there may be some complications, but in principle, it's pretty easy. So mu is proportional to logarithm of I0 divided by I1, and x does not play much role here because it's just a scaling factor. So suppose you do measure it. Suppose you do measure mu in pretty broad energy range. How will it look like? It appears that it looks something like this. For different pure samples that contain only one chemical element, like let's say copper, only platinum, only palladium, the spectra look like this. You see a steady downward trend with some very sharp steps, jumps. And these jumps, these peaks, we call them X-ray absorption edges. And you see that for different elements, these absorption edges are positioned at different energies. So the titanium edge is different from copper edge, and it's different from platinum edge, and so on. So somehow the edge energy is a characteristic feature of a particular chemical element. That already gives a clue about the element selectivity of the methods that we'll talk about later. So X-ray absorption coefficient is a measure of how much the sample absorbs X-ray light. So it means that when we have an edge jump, X-ray absorption step, it means that we start absorbing more energy abruptly. So where this energy goes, what is it used for? Because the energy should be conserved, right? So we should use it for something. And it appears that we use this energy for electronic transition, for photoelectric effect. So the electrons, the core electrons, are promoted from core levels to the unoccupied states. As soon as the energy of incoming photons becomes sufficient to kick the electron out of a particular core level to the unoccupied states, the photons start getting absorbed resonantly, and the absorption coefficient jumps. It increases abruptly, creating what we call X-ray absorption step, X-ray absorption edge. And different edges are called, they have different names. You see this K, L, 1, 2, 3, M, 1, 2, 3, 4, 5. So this nomenclature is meant to indicate the core level from which the transition occurred. So when we talk about, for example, L3 edge, we mean that the transition comes from 2p3 halves. And when we talk about K edge, it means that the transition comes from 1s level. So here, if we zoom in, yeah, copper K edge, again, that means that the transition is from copper 1s level to the free orbitals localized around copper atoms. Let's zoom in further into the edge. If we do, we see that it's not as simple as it looks like, and the edge actually contains some structure. So the absorption is a variation of absorption coefficient. Slightly before and after the edge, it has some oscillations. So from Fermi-Golden rule, we know that the absorption coefficient is basically a matrix element multiplied by the density of unoccupied states. And the oscillations after the age, they come basically either from the variation of the, or before the age, either from the variation of the density of state or from the slow variations of the matrix element, which where basically you have the final wave function of the final state, which is a sum of the wave function of outgoing wave, photoelectron wave, from the it's electrons that got ejected from the core, and the backscattered, so outgoing wave, and the backscattered wave, the same wave backscattered from the neighbors of the absorbing atom. And the interference of these two waves creates this oscillatory pattern. So due to slightly different physics behind and the different methods of the analysis, XAS spectrum, X-ray absorption fine structure, is usually divided in two distinct parts. The part that is below the edge and a little bit after the edge, something like 30, 40 electron volts after the edge, is called XANES, X-ray absorption near-edge structure. In the soft X-ray community, sometimes people call it EXAFS, near-edge X-ray absorption spectra. So it's basically XANES and EXAFS is the same thing. And it's basically a reflection of the density of unoccupied states of your absorbing atoms. And these spectra contain information about local geometry and the oxidation state of the absorbing species. The other part, the further away part, that is further away from the edge, this oscillatory part, and is called the extended X-ray absorption fine structure, EXAFS. And as I said before, it's due to the interference between the outgoing photoelectron waves and backscattering one. So that's what creates these ripples. And these oscillations being Fourier transformed, they give you something that resembles the radial distribution function. It's not exactly a radial distribution function, but it's something pretty close to it. So it contains information about bond distances, coordination numbers, and also disorder of your material. So the things to remember about XAS that it is an element selective technique. So it probes only the species of selected element. Why? Well, because you measure a particular edge, you select which edge to measure. So if you measure a platinum L3 edge, that means that you sit on your platinum atoms inside your sample and you look around and you see only things that are around your platinum atoms. You see their neighbors, but you don't see anything that is maybe further away than, let's say, 5, maybe 7 angstrom from it. No, you see only the local environment of a particular species of particular chemical element that is the one whose edge you measure. But it has a particular consequence that the technique is an averaging technique. So it probes all the species of selected element. So if you have different, so you're talking about platinum, right? Different oxidation state of platinum, platinum 2 and platinum 4 in your sample. When you measure platinum L3 edge, you will have a contribution from both species, both oxidation states into in your data. So basically, your XANES spectrum, your XAS spectrum, is a linear combination of the spectra of different non-equivalent species of particular element present in your sample. So the same. It's not only about the oxidation state, but also about the local environment. If you have different species of the same element, different species that have different local environment, well, in your XAS spectra, you will see the contribution of all of them. And the weight of these contributions will be proportional to the abundance of this relative abundance of this species in your sample, part of the sample that is exposed to the X-ray beam. And of course, why we like this method is because it contains electronic and structural information about the absorbing species, oxidation state, coordination geometry, local disorder, and so on. As a quick overview, here you can see the XAS spectra of 3 different copper compounds in solution. So copper in water surrounded by 6 water molecules, and 2 copper ammonia complexes, copper 2 and copper 1, that are different by the number of ligands, and also the average bond distances of all 3 of these compounds is different. So what you see is that on the left panel, XANES spectra of all 3 of them are very different, because basically everything about them is different, apart from that they contain copper, right? So the symmetry is different, oxidation state for 2 of them is different, the number of ligands is different. So the XANES spectra are different. And for each, well, for many elements, for many particular species, there are some particular traits of the spectra that you can use to assign the spectrum to particular species. For example, here in copper, there are 2 things. So first of all, this huge peak for copper 1, it's characteristic for linear species. For copper 1 in linear geometry, so looking at this spectrum, we can already say that we have something like this linear diamino complex in our sample. And another very important signature of copper KH is this little pre-H peak on the left, which is a transition from, it occurs because of the transition from 1s to 3d of copper 2. And you see that it is present for copper 2 because there are some empty states at 3D, and it's completely absent for copper 1 because for copper 1 the 3D is filled, so the transition is not possible. So this is a way to discriminate between copper 1 and copper 2 from XANES. And from EXAFS, you also see that the EXAFS Fourier transform shows you that the number of ligands is different, and you see the intensity of this main maximum is proportional to the number of nearest neighbors, 2 for diamino, 4 for tetraamino, and 6 for copper hydration shell. But also the position of this maxima is different, and that reflects the different average bond lengths of the species. But we'll talk about all this in more detail slightly later. So first, let's have a look at in more detail into XANES. So XANES spectra, they consist of the pre-H region, so something that is a structure that is before the main maximum, the edge, and the post-edge. So pre-edge very often contains information about the symmetry or and oxidation state of the absorber. The edge position is often used to define the absorber oxidation state again. And the post-edge is a signature of particular geometry, and contains the details and can reveal the details about the local atomic structure and geometry. But to analyze it quantitatively, it can be sometimes computationally demanding. Well, there are different ways to do so, which we'll discuss. So starting from the pre-H peak, you see that, for example, for the 3D metals, it's particularly visible that for different symmetry, you can have very different pre-H, like here for titanium 4+, depending on the octahedral or tetrahedral environment of titanium, you can see that the pre-age intensity is very different. It happens because for octahedral titanium, this 1s to 3d transition, that is the reason why this pre-age occurs. It's basically forbidden. Well, it's always but dipole forbidden. But in tetrahedral geometry, you can have some mixing between the 3D and 4P, and so the transition becomes possible. And so it becomes possible in tetrahedral case because of this hybridization of orbitals. So the 3D gets some 4P character and the intensity jumps a lot. So just looking at this data, at this spectrum, you can already say whether your material titanium is octahedral or tetrahedral. And that's already can be a very important piece of information. And this is true for many 3D metals. So you see basically for less symmetric environments, for tetrahedral environments, the intensity of the pre-age is much higher. So pre-age can be important signature of the symmetry of the absorbing species in your material. The edge position is very often used to assess the so-called chemical shift. So what we call chemical shift in XAS has nothing to do with chemical shift of NMR. It's just a shift of the X-ray absorption edge because of the difference in the oxidation state. So the absorption edge usually shifts when the oxidation state changes. So the higher is the absorber oxidation state, usually the higher is the absorption edge energy. So you see here in all this example, copper, manganese, cobalt, palladium, the species with higher oxidation state has the onset of the edge at the energy that is a little bit higher, which, I mean, it is relatively easy to understand because what we do when we see an X-ray absorption edge, we eject an electron from the core, and the higher the oxidation state, the fewer electrons are around the core. So the higher the screening of the core, so the harder it is to eject one more electron. So the more energy it takes, just because all the electrons are interacting more with the nucleus because the screening is lower. So this is the properties that is very, very often used in the analysis of XAS data. So you see the shift of the edge. It says about something gets oxidized or reduced. So this is very, very common. So coming to some examples, let's say from the most basic to a little bit more sophisticated ones. So starting from the most basic, well, we said that the XAS spectra, XANES spectra are like fingerprints of our materials. So they are sensitive to local geometry, oxidation state, everything. So they are like fingerprints. So we can use them as fingerprints. So imagine you have a materials. In this case, it's a metal organic framework that contains solvent in its pores when it is as synthesized, and then we can dissolvate it by heating. We heat it and the solvent goes away and the structure changes a little bit. What happens with the cerium ions that constitute the cornerstone of the smoke? Does the oxidation state change? What happens with them? Well, the answer can be provided by XAS, by XANES actually. So we can measure the reference spectra of cerium compounds of well-defined oxidation state. Like here you have the spectrum of cerium oxide and the spectrum of cerium nitrate. Cerium oxide is cerium 4+ and cerium nitrate is cerium 3+. And then we measure the spectrum of our MOF, metal organic framework, before desolvation, so fully solvated one, and after desolvation, so desolvated. And already, even not being a big expert in XAS, you can probably guess that cerium remains cerium 3. Cerium in our material remains cerium 3 upon desolvation. Similar example is with palladium nanoparticles. So when they're exposed to hydrogen, you form palladium hydride. When they're exposed to acetylene, they form palladium carbide. But what happens if you expose them to a particular mixture of hydrogen and acetylene? So who wins? Again, we do the same thing. We measure the particles in an atmosphere of pure hydrogen, an atmosphere of pure acetylene, and also in vacuum when there is nothing, when we just have a metallic palladium. Since the difference in the spectra is not very pronounced, we can also have a look at difference spectra, which is more easy to see. So the difference is more easy to see between the hydride and carbide. And then we measure a spectrum in a mixture of hydrogen and acetylene. Again, we make a different spectrum with respect to the vacuum, to the palladium in vacuum, so purely metallic palladium. And we see that the spectrum of our species very closely resembles the one of palladium hydride and not at all the one of palladium carbide. And this is our conclusion, this is our result, and that in this particular mixture we form hydride and not carbide. And this approach can be used not only in a, let's say, single point, a single set of experimental conditions. It can be used to track the evolution of the speciation in your material during a particular chemical process. So in this case, this example is about copper zeolites, copper mordenite during the protocol of methane to methanol conversion. Here, from previous studies, we suspect that during this protocol, our copper can form 3 different species inside the pores of our zeolite. You see the red, the black, and the blue spectra. The blue is a hydrated copper. The black one is the copper ions coordinated to the mordenite framework, and the red ones are the copper one coordinated to mordenite framework. So mobile copper 2, framework coordinated copper 2, and framework coordinated copper 1. When we measure the spectra during our protocol under in situ conditions, we can use these 3 reference spectra to do a linear combination analysis. So to represent the spectrum of our sample as a linear combination of 3 different spectra, these 3 different reference spectra. And you see that the agreement for these 2 particular illustrations is pretty nice. So the approach is not hopeless. And doing this for every step of the protocol, we can see how the structure of our material evolves, how the speciation evolves. So when you see that in, when it is exposed to methane, you have the growth of copper 1 fraction. So the copper continuously reduces. And then in the end, when you expose expose it to water vapor, of course, you have the fraction of hydrated copper that increases. So all this can be tracked, and you can also tell the difference between the different samples, because these two plots are two different samples. So you see that they behave differently. One of them is more prone to form copper 1 than the other, and that may explain the difference in their catalytic activity, in their productivity. But so this approach, linear combination fitting, is very powerful, but it has one very important disadvantage, that you need to know the spectra of reference compounds beforehand. And sometimes you don't have this knowledge, or this knowledge is incomplete, so you don't know the spectra of all the reference compounds. In order to deal with it, there are some other methods like principal component analysis that can give you a hint of the number of different species in your sample, and multivariate curve resolution, MCRLS, that can give you the spectra of the independent species that form your that participate in your spectrum, that form your spectrum, constitute your spectrum. As an illustration of this, here there is another example on copper mordenite. So two different samples measured during the thermal activation, so heating, in oxygen or in helium. So 4 sets of data, 4 sequences of spectra, 2 samples and 2 conditions. And when all the spectra are fed to the MCRLS algorithm, with the prior knowledge about the number of different species, and this knowledge is obtained by principal component analysis, you can get a set of independent spectra, the spectra of independent species that constitute all this data set. So all this spectra inside the data set can be represented as a linear combination of these 5 species. Here the problem is that the mathematical algorithm does not know anything about XANES. So these spectra that you see here in the center, they are purely mathematical things. So it's up to you to decide whether they are meaningful, and if they are, what they mean. Of course, there are some constraints that we can put on the fit, like we can constrain the spectra to be not negative. We can constrain the sum of the weights to be equal to 1. But as for the rest, it is up to you. So it cannot be a first thing that you do to study your sample. You need to have some prior knowledge. And in this case, this prior knowledge was present from calculations, from different other techniques, from other XAS experiments in more controlled conditions. So we knew that, for example, the red spectrum is the spectrum of the linear copper 1, or the blue spectrum is the spectrum of hydrated copper, and so on. And when we know all this, you can put some meaning into the concentration profiles that you obtain, because apart from these 5 spectra you obtain, how do their weights change during your protocol? And here, for example, the difference is quite pronounced for the 2 samples, and the difference in the productivity, again, the difference is the productivity of these 2 samples for the methane to methanol reaction was closely connected to the different abundance of particular species. And this is actually very important, because as we said in the beginning, the goal is to determine how does the property depend on the structure, and this is a way to explain the properties of the samples. So why one sample behaves better than the other, why it is more productive, why it works better. And often the answer comes from the structure, and in this case, the XAS gave an answer why one sample works better than the other. Well, because the abundance of particular species that does the job is higher in one sample than in the other. So the good things about XANES is that it can be calculated also. And this is a very promising way to get quantitative information about different structural parameters. So here, for example, we have this linear copper species, linear diamine species. And when we calculate the spectrum, we can see that the agreement is pretty nice. And we can also see, but we vary the distances between copper and nitrogens. We can see how does the spectrum change. And by tuning this distance to get the best agreement with the experiment in the calculated data, we can conclude about the best value, the most appropriate value of the structural parameter. So we can tell which is this bond distance. But here the difficulty is first that to calculate the XANES spectrum, we need to have a model, a preliminary model that you can obtain from either from a DFT or from diffraction, from any other input data that you can have. So you need to have a coordinates of atoms. And then the other thing is that calculating XANES is not an easy thing. It can be done by different codes, very sophisticated codes. The most popular ones probably being FEF from University of Washington in Seattle, in the US, and FDMNS from CNRS, from Grenoble, from just next door from here. Actually, the author of FDMNS usually will give a tutorial, I think, this afternoon. So if you are, probably it's already too late to subscribe, but well, those of you who subscribed, you will enjoy it, hopefully. So it's a very, very, very powerful code that can do a lot of things. And one of the things that it can do is to calculate XANES spectra very, very well. And of course, this computational, the possibility to calculate spectra and the possibility to link the spectral shape with the values of structural parameters, now it is heavily exploited by different machine learning techniques. So the more powerful the computer becomes, the faster you can calculate the spectra, the more spectra you can calculate. And then you have the big data, and then you can analyze the big data by different machine learning algorithms. And that's now it's a very, very hot topic, hot direction, let's say, and it's developing very, very fast, which is very good. Then let's discuss a little bit about the EXAFS, extended X-ray absorption fine structure. But before analyzing the EXAFS, first we need to extract it. The XANES is pretty straightforward. With EXAFS, you need to do a little bit more to get this nice EXAFS oscillation. So you need first to normalize the data. So usually in the most codes that do this, you have to define the pre-edge line, so-called pre-edge line, that is here is a blue line, which is the fit of the pre-edge range, flat region for the edge jump. You should define the post edge line, which is a fit, a spline. Usually it's a parabola or it can be a straight line through the oscillatory part of the data. And you have to define the edge energy, E0, which is usually defined as the maximum of the first derivative of the spectrum that is on the edge. But there is no fundamental law of nature that tells it has to be exactly there. So you can define it in a consistent way throughout your data set. And as you will see later, you will refine this value. So it's not extremely important to be super precise defining zero. It has to be done in a consistent way for all the spectra in the data set. And then you will see that it will be fine. And then by defining the pre-edge line, a post-edge line, and edge energy, you can calculate the edge jump, which is basically the difference between the post-edge line and pre-edge line at the E0 energy, at the edge energy. And this edge jump can be used, should be used for normalization. So to get the EXAFS data, you subtract your actual data from the atomic background that is calculated by, there are different methods to do so, but basically it's done by a code that you use. It is needed to subtract the part of the signal that is not structural, so it does not have any structural information from there in it. So you subtract it from the data, it's generated by your analysis software, and you normalize by the edge jump. And another thing that you have to do is to convert from the energy domain to the wave number domain, because, well, we will be looking at the interference pattern of photoelectron. It does not make much sense to stay in the energy scale of the incoming photon. So since we're going to deal with electron, we pass to the wave number domain, so wave number of this electron, and the conversion is pretty straightforward. Here's the, E is the energy of your incoming photons, and E0 is the edge energy that you defined. So the definition of E0, it influences the zero of your wave number scale. But here, and here we are actually, we did the job, we did all this for this very beautiful spectrum of palladium K edge, and you see our data, that's already EXAFS data, EXAFS function chi of k is called. And the data are very clean, but there is some problem that actually above like K10, you don't see much, right? So you don't see so many, you don't see the oscillations, they are not very intense. So what is usually done in an XAS analysis is that we multiply the spectrum by K in the power of something, usually 2 or 3, to see better the data. So here we multiply the data by K cube, so the data weighted by K cube, and then you see that the data contain a whole lot of structure here. You can see the signal up to K20, 19. And we will analyze the data within this window, depicted in red here, the red curve. So we cut the low K and we cut the high K where we already might have a lot of noise, or we are not very sure about the atomic background generated by our code, because in the end of the spectrum, it can be already imprecise. So, but this is it. We have our EXAFS spectrum, EXAFS oscillatory pattern, and now we have very little to do. We just need to analyze it. We just need to fit it. Okay, very little is probably an understatement. So we have a lot to do. And here, how are we going to do it? So we say that this signal contains information about the interatomic numbers, interatomic distances, coordination numbers, and so on. So we hope to come up with an analytical expression to describe this signal. So a function of structural parameters that gives us this signal. And then we can minimize the discrepancy between the experimental spectrum and our theoretical one by varying the parameters in this analytical expression that we come up with. And that's what we call fitting. Because then if the agreement is good in the end, then it means that the parameters of our analytical expression are correct. And among these parameters, hopefully we will have coordination numbers, interatomic distances, and so on. So to start with, the signal closely resembles a periodic function. Modulated one, but still it's a periodic function. So we can already safely assume that EXAFS function is a periodic, EXAFS signal is a periodic function of K. So we should have a sine or cosine of K, where K is a photoelectron wave number. We discussed before that the periodic signal is an interference between the outgoing and the backscattered waves. So the condition for constructive interference in such case is that the two interatomic distances should be equal to an integer number of wavelengths of our photoelectron. Combined it with the definition of the wave number, we can get the interference condition, and this interference condition would be satisfied if you put the 2R as a frequency in our expression. So we're going to have a cosine of 2RK. Then the scattering probability depends on the atomic species. So when we have the blue and orange atoms on the left, you have the particular probability of the orange atom to backscatter the photoelectron wave towards the blue atom. But if instead of the orange atom, you have the green atom, so a heavier one, the probability to backscatter will be higher. And that means that we need to introduce a particular factor that is called the scattering amplitude into our expression. And it depends on the atomic species. Usually, the more electrons the atom has, the heavier it is, the greater is the scattering amplitude. So if you have your absorber surrounded by nitrogens, the signal will be weaker than if you have the same absorber surrounded by bromines, for example. But also, it's not just a scaling factor. The scattering amplitude depends also on K. It's a function of K. So the dependence is a little bit more complex. It's not just a scaling. It's not just scaling. It's usually also a shift towards a higher K. The intensity, the maximum amplitude shifts to high K for heavier atoms. But the most pronounced effect is the increase of the intensity when you have heavier neighbors. Then the resulting signal is basically a sum of all the signals coming from different scatterers. So if you have the orange neighbor at distance R1 and the green neighbor at distance R2, well, you will have a sum in your signal. This signal will be a sum of the two contributions. And then the neighbors can be combined into a different coordination shells, because it happens pretty often in the materials that the atoms of particular type are at the same distance from atoms of the other type. Crystals, for example, happens quite often, and so they form coordination shells. And then instead of summing all over all the atoms, we can sum over different coordination shells and put the coordination number, basically the number of atoms in particular shell, inside the sum here. So here already we start having our meaningful parameters, so coordination numbers in the particular neighboring shell. Another possibility that we can have in the EXAFS data is so-called multiple scattering. It happens when, for example, this signal from the blue atom for outgoing photoelectron wave coming from the blue atom, that is the absorber, goes to the green atom and gets backscattered. Scattered wave is a spherical wave. It goes everywhere. Part of it goes back to the blue atom and we see the single scattering, but part of it goes to the orange atom, which is at R2 distance, and then it gets scattered from the orange atom, and then it goes all over again, and some fraction of this doubly backscattered wave goes back to the blue atom. So we can see sometimes the contribution from this multiple scatterings, the scattering that contains multiple neighbors. And here, basically, what we need to do is redefine R. To stay general, we redefine R that we had in our expression as a bond distance. Now we're going to call it not, we're going to define it not as a bond distance, but as a half length of the total scattering path. If it's a bond distance, for a single scattering, the scattering path is twice the bond distance. So half length is, it stays a bond distance. But in case of multiple scattering, it's going to be half length of the whole path. So R1 plus R2 plus R3 divided by 2. Then it so happens that when the photoelectron wave propagates and scatters, its phase may change. And this has to be taken into account in our analytical expression. So we have to introduce the phase shifts, which are element dependent and also K dependent. Okay. Then as I said already before, the EXAFS in EXAFS, the outgoing and backscattered waves, they are spherical waves. So the scattering probability goes down as R squared. And we can show it explicitly in the EXAFS equation. Here we have R squared in denominator, and we put also K in denominator as a matter of convention, which requires redefining f of K. The photoelectron wave also undergoes some losses during the propagation. It can be intrinsic losses. So because we can have, for example, multi-electron excitations during the absorption of the photons. And this is taken into account by a zero squared term inside our equation. And we can also have extrinsic losses. So the photoelectron wave can decay due to the inelastic scattering, or during the propagation, also because of the decay of the core hole. And this is taken into account by this exponential term, where lambda is photoelectron mean free path. Then we should also remember that when we say that the distance between the atoms, particular atoms like the blue and the orange atom, is R, well, in reality, this distance is not as precise as we'd like to, because first, the atoms, they vibrate just because it's warm around. So there is thermal vibration, and the warmer it is, the more they vibrate. But the other thing is that in the same coordination shell, the distances between different atoms and the absorbing atom can be slightly different. Not too much, because we still call it a coordination shell, but a little bit different. And this we call a static disorder, and also contributes to the basically an error in the determination of the interatomic distances. So this error, this imprecision, is taken into account by introducing so-called the Debye-Waller factor sigma squared into the EXAFS equation. And basically that's it. If you're not talking about accumulants, that's what you have. That's the EXAFS equation. And here, the good part of EXAFS, the nice thing about EXAFS is that actually all of the terms in the EXAFS equation can be either calculated, like the scattering amplitude, the mean free path, and phase shifts. The most common software to calculate it is again FAN. So you can either calculate, so you either calculate some terms like these terms and recalculate, or the other terms, you fit them. And these fitted terms, some of them are actually what you are looking for. So the atomic distances are the Debye-Waller factors that are a measure of disorder and coordination numbers. To illustrate how it works, let's have a look at this molecule of piperidine, functionalized with palladium, with coordinated also with some chlorine atoms. So this is a linker for a moth. When we measure EXAFS data, the data are very nice. You can measure up to very high K, and you can fit this data very nicely with two different shells, contribution of two different shells, palladium nitrogen and palladium chlorine, with a coordination number of 2 for both of them. And you can get a very nice agreement with the experiment, and you can get the values of the coordination numbers and the bond distances. On this example, let's see how different parameters influence the spectrum, the EXAFS spectrum, because this is very useful to understand how actually to have this feeling of the parameters, of different parameters. So when we change the parameter R slightly, the interatomic distances, let's change it for chlorine in our example a little bit by 0.02 angstrom. And you see that the whole pattern shifts. The shift is more pronounced at high K, but it's clearly visible. So the EXAFS is basically an interferometer. It is very precise, and it can detect all, even a very slight changes in interatomic distances. So 0.02 angstrom is clearly visible in EXAFS. So let's have a look at E0. The hidden parameter, it's not present in the EXAFS equation. You remember that to get to the K domain, had to use E0, the onset of the edge energy, to convert between the energy scale of the photon and the wave number scale of the photoelectron. So E0 is important, and it influences actually quite a lot the data. So if we change the E0 by 5 electron volts with respect to what we set as the maximum of the first derivative for the palladium KH for this particular spectrum, you can see that the whole picture changes. The shift this time is more pronounced at low K, but E0 is something that we fit during the fitting. It's one of the fitting parameters. That's why before I said that it has to be chosen consistently for the spectra of your data set, but it's not super important for EXAFS fitting. It's not super important to guess somehow its really precise value. So you don't know it. You cannot know the exact value of E0 before you do the fitting. And when you do the fitting, you refine your E0, and then you are fine. The Debye-Waller factor, if we change it a little bit, we increase it a little bit from what we got initially during the fitting, and you see that this slight increase, the substantial increase of the Debye-Waller factor, it leads to a decrease of the intensity of the spectrum. So the decrease is more pronounced at high K. So you see that the oscillations are damped. So that explains actually the effect that we see during the measurement at high temperature. So when we heat our material, well, the oscillations in EXAFS, they got damped, they got less intense, and that's because the atoms start vibrating much more, and this is due to the increase of the Debye-Waller factor. That's 0 squared. If we change it a little bit by 20%, we see that since it's just a scaling factor here, we see that there is a uniform change of amplitude. So the whole signal gets increased by 20%. And let's do the same with coordination numbers. Let's change N chlorine by 0.4, again, by the same 20% from 2 to 0.4. And you see that the effect of increasing N by 20%, it is the same as for increasing S0 squared. Why? Well, if you have a look at the equation, you can see that basically the S0 squared and N, they are correlated by 100%. So you cannot actually fit both of these parameters. You have to fix one and fit the other because the correlation is really 100%. So the change of N by factor of X gives exactly the same result as the change of S0 squared by factor of X. That's an important issue that has to be taken into account. So to see the effect of scattering amplitude and phases, let's substitute in our model the chlorine with bromine, keeping the bond distances the same. So you can see that when you have a bromine, the whole pattern shifts in K and also gets quite more intense. So that's why bromine has a different scattering amplitude and causes different phase shifts. As I said, well, bromine is heavier than chlorine, so the signal becomes more intense. So to do the fitting, we have to also introduce something that tells us whether our fit is good or not. And this goodness of fit is actually called in EXAFS, it's called chi-squared. It's represented by this formula where epsilon is the uncertainty of the measurement, which is evaluated automatically, usually by the code. And for a given spectrum, it influences the value of chi-squared, but since it doesn't change with the structural parameters, it's just a scaling factor, so it does not change the minimum. And here chi-squared, it's not chi of k. We just ran out of letters, so it's not the same chi. So chi of k is a signal, chi-squared is a measure of goodness of fit, but it's not the same thing. Okay. So then we also talk about reduced chi-squared, because the more parameters you use for your fitting, the better your result may be, but it can be not justified, right? So you can get better result not because you describe your properties better, but just because I have more parameters. So in order to take this into account, the reduced chi-squared was introduced, which is basically chi-squared divided by the difference between the number of independent points and the number of parameters that you use in your fitting. And number of independent points is determined by a Nyquist criterion, which is basically the amount of information that is contained in your spectrum. And of course, it's better to keep the difference between N IND and N par as high as possible. So you should not use too many parameters. How many is too many is defined by the maximum value that you may have, that's NIND. So normally the codes that you use for EXAFS fitting, they give you this these values. So you can have they calculate use as a number of independent points, so you can have an idea of whether you're using too many parameters or not. And this number, reduced chi-square, is basically it's actually the figure of merit that is used in the fitting. But what is most commonly reported is the R factor. So it's reported like this. And usually, if your R factor is higher than 3%, that means that there is something wrong with you, most probably. So the good fit should have an R factor at least lower than something like 3%, better lower than 1%. But if it's higher than 3, then most probably the fit is not good. Then we might have another problem, because for each scattering path, we need minimum 5 fitting parameters, right? We are talking about S0 squared, I0, and delta R and sigma squared. Okay, so from the Nyquist criterion, we know that NIND is around 20, something like this, from 10 to 40. So the order of magnitude is like this. That means that if you have something like 3-4 shells, already we can be out of business completely. Well, it's not so. It seems so, but it's not so, because we can use common sense and prior knowledge to decrease the number of parameters that we use for fit. For example, for E0, we use most often 1 parameter for all paths, because E0, or let's say delta E0, is basically the error that we introduce by choosing the edge energy. So when we normalize the data, we say the edge energy is here. Maybe we are wrong. So we made a mistake, okay, and we correct this mistake during the fitting. But this error is the same for all the scattering paths, so there is no reason to have different I0s for different scattering paths inside the same fit, unless we have some particular cases where the actual spectrum is a combination of the spectra of the species with a very large difference in the edge position. So imagine you can have a very different oxidation state for 2 different species inside one sample. And so when you take this into account in EXAFS, then yes, you should have different E0 for these 2 species. But this is a particular case. In general, the E0 is kept the same. Then for S0 squared and N, we have no other choice but to fit one and fix the other. And here we need a prior knowledge. So we can get coordination numbers, for example, from diffraction, from DFT, and fit S0 squared. Or we can get S0 squared from EXAFS fit of the known compound. I'll show it a little bit later. So if you have a compound that you know should be pretty similar to your sample, and in this compound you know what coordination numbers are, you can fit this compound by fixing coordination number, obtain the S0 squared from this reference compound, and then use this value of S0 squared for fitting your actual sample. And there you can, in this fit, you can fit the coordination numbers because your S0 squared is fixed. For delta R, well, you should use independent parameters for important paths. Yeah, this is clear because it's mostly what you are looking for when you do the fitting. If you are sure about the symmetry of your system, because you got it, for example, from diffraction, you can use geometrical constraints on delta R, like in the example on the right. If you know that the system keeps this symmetry, then you don't have to fit R1 and R2 as independent parameters. You can fit delta R2 as a square root of 2 times delta R1, if you know that the symmetry is going to be conserved. Then sometimes for, let's say, less important paths of further away shells, sometimes you can use the isotropic contraction expansion model just to have this slightly better agreement with the data, to have the better background created by multiple paths, multiple very weakly contributing paths. So you can have this approximation like delta R is equal to alpha R for many paths. So you can fit many paths with just one parameter alpha, which is the isotropic expansion contraction factor. So this is justified for cubic systems. For systems which are less symmetric, it's probably a little bit less justified, but still it may be an option to consider. For the Debye-Waller factor, again, for important paths, it's often inevitable to have the independent parameters. You can try to assign the same Debye-Waller factor to similar paths, similar in terms of bond lengths and the ligands. Then you can use also, sometimes there can be analytical expressions for particular paths, and sometimes you can use the models for dependence of sigma squared, for example, on temperature. Like here, it's an Einstein model, which shows you the dependence of the Debye-Waller factor on temperature. The common problems that we usually have is EXAFS fitting is correlations. The most drastic example is correlation between S0 squared and N, coordination number. It's always 100%. You cannot do anything about it. So it's always there. But also there are quite strong correlations between amplitude parameters, so S0 squared and sigma squared, because both of them act on the amplitude of the data, and what I call phase parameters between E0 and R, because both of them shift the spectrum. So when you have only one shell fitting, sometimes this correlation are quite strong, and that of course increases the error of your fitting and makes the fit less robust. So the solution can be fit multiple shells, but even then, these correlations can be quite important. So you can also have correlations between amplitude and phase parameters because of the constructive and destructive interference of the signals coming from different paths. So it's possible to have the correlations also between amplitude and phase parameters. So what to do about them? The best thing is to use prior knowledge to fix some of the parameters, because if the two are correlating, but you know that one can have a particular value given by some other techniques that you used, well, fix these parameters and that would fix the correlation. You can include multiple paths in your fit, because some parameters are common for different paths and some aren't. And if you include multiple paths, then there will be less possibility for correlation. If possible, you can do multi-sample or multi-edge fitting, because this also will allow you to use the same parameters with larger data set. And this will fix some of the correlations, that may fix some of the correlations. So usually the higher is your number of parameters, the higher problem, the bigger problem with correlations you have. So these are the strategies that can help to reduce the correlations. So talking about the codes to do the job, well, most common and in my opinion, the most user-friendly, the most instructive code to do the job is Demeter package. That means Athena and Artemis, the top parts of this package. So Athena is used for data normalization, plotting of XANES and EXAFS. So basically, it's used for looking at the data for aligning the data, for deglitching. And Artemis is used for EXAFS fitting. That is where you introduce the different paths, you do the calculation of phases and amplitudes. Well, you do it with FEF, but it is integrated as an Artemis module. And then the Hephaestus is very useful XAS database. It is part of the same Demeter package. Unfortunately, the last version of Demeter was issued quite a long time ago, so it's not regularly updated, unfortunately. But still, for being a free software, it's a fantastic piece of software. And if you don't have a lot of XAS data, you have maybe up to 100 spectra, maybe 50 spectra, there is hardly a better way to look at them, just to get the feeling of different K weights, different normalizations. So it's very, very, very nice software. When you have the big data, you have a lot of XAS spectra, then it doesn't work anymore. So then I had trouble handling more than something like 50 spectra with 50 references. And also you will have trouble looking at the spectra one by one. It's more difficult. So when you have a big data, a lot of XAS spectrum, then one of the most widely used software is Large. It's called Large, coming from Matt Newell from Chicago. It's a Python, basically it's a Python environment that can be used as a standalone software, or it can be used as its modules can be used as a Python libraries. Basically, you can do your Python scripts for analysis of the data, where you can use the Large libraries. It's a very, very powerful tool, and it's actively developed by Matt and also by other contributors. It's very, very powerful, but this is probably for more advanced users. It has a graphical user interface. It's called XAS viewer, I think, but you can try it if you just to get an idea of it. But if you're a beginner, try with Athena, start with Athena, and then you will see whether you need something else or not. But it's learn with Athena first, and then see for yourself whether you want something else. Good. So we are, I think, reaching almost the equator, and I suggest to do a short break. Okay, here we are. Welcome back. Now I would like to discuss some EXAFS case studies, to present some EXAFS case studies. But before, important piece of information. So you have a Q&A box in Zoom, right, to ask questions. So please do not hesitate to do so, because I hope that in the end we'll have some reasonable time for questions and hopefully answers until you stop having the questions. I think we'll have quite a lot of time, but there should be an option when you ask questions in Q&A box. There should be an option to upvote all questions of others. So before asking, just have a look. Maybe someone else has already asked this. In such a case, just put a like on it, or I don't know whether it's a like or whatever, a thumbs up, whatever thing. So there is a way to upvote them by clicking on them, and in such a way, the most upvoted questions, they'll go on top, and I'll try to answer them first. And our host hopefully will help me with this, with identifying such questions. So please do so. Use use Q&A box and do upvote the questions of others if you think that these questions are interesting or pertinent and generally want them answered. And then I will do my best. Okay, so coming to EXAFS case studies, okay, yeah, I see the first question coming in, but we will try to do it in the end, okay? Because otherwise it will you can ask them already, yeah, okay, and there is a thumbs up button now. I see it. I will answer them in the end, but you can start asking already now, and then in the end we will come to this. So case studies, right? The first one is about the metal organic frameworks. Again, we do quite a lot of them. It's about the mixed metal UIO 66 metal organic framework, which has the cerium and zirconium in the cornerstones. So this MOF is a cubic MOF, which has inorganic linkers, the octahedra, zirconium octahedra, in its, let's say, classical plain vanilla version. Zirconia octahedra that are interconnected by organic linkers. And what makes this MOF so special, is quite famous in the world of MOFs. It was one of the first MOFs that was stable at high temperatures. So it's very stable, and it has quite a large surface area. So it's that makes it promising for different applications. And the thing is that zirconium by itself is not very redox active. So for catalysis is a little bit, it's hard to use it for some redox applications the way it is, this octahedra, this zirconium oxide octahedra. And so one of the ideas that came later was to substitute the zirconium with something that is redox active, for example, with cerium. So it appears that it's possible to synthesize the MOF with one or all of the zirconium substituted by cerium. One atom in the octahedra, or all of them. So it depends how much cerium you put in the synthesis. I mean, so far we don't know yet whether it's one atom or several, but synthesizing the material with different amount of cerium, you get the crystalline structure. And this fantastic work was done in the group of Norbert Stock, Professor Stock and Kiel. And well, actually, we see that the amount of cerium influences quite a lot the stability of the material. You see that the more cerium we have, the less, the lower temperature it withstands. But this dependence is far from being straightforward. You see that first it decreases quite sharply down, and then at around like 20% of cerium. Here we always talk about cerium in percent with respect to the total metal content, and the rest being zirconium. So 20 means that there are like 20% of cerium atoms and 80% of zirconium atoms in the cornerstones. So it's around 20%, it levels off. So that looks at least not obvious. And the questions that arise already, like, okay, the main question is why it happens. Then the easier question, or conceptually easier question, for which we don't know an answer yet, we didn't know an answer, is whether something like this happens. So you can have, when you have like 20% of cerium in the cornerstones, what does it mean when you have some? You have 20% of cornerstones that are pure cerium and 80% of cornerstones that are purely zirconium. Or you can have a mixture of cerium and zirconium in one cornerstone. So when you have a partial, when you have both metals, do you have the mixture of different metals inside one cornerstone? This question was not answered at that time, so there was no answer. Nobody knew it for sure. And the method that can give an answer, straightforward answer, very clear and unambiguous answer is X-ray absorption spectroscopy, because we do see the different contributions, the different neighbors of this heavy metal, zirconium and cerium, if we measure cerium or zirconium key edges. So we are very sensitive to the nearest neighbors. And of course, we can, since cerium and zirconium, they're very different, they're quite different, number of electrons quite different, phases and amplitudes are quite different, we can discriminate easily between the cerium and zirconium neighbors. So in order to answer these questions, this is a small question, whether like, we have the situation on the left or situation on the right, and bigger question of like what happens in general. We measured the spectra of different mixed metal MOFs, UIO 66 MOFs, with different cerium content. And so ranging from, let's say, measured pure compounds, and also those that have 10, 22, 45, 84% of cerium. And we measure them at both zirconium KH and cerium KH. So the same compound was measured at two different ages. And here are the data. These are the Fourier transform EXAFS data on zirconium and cerium KH for 6 different samples, 2 pure ones and 4 mixed metal ones. And already just looking at this data without any analysis, already it's clear that this scenario does not work. It simply does not work because the spectra are different. If we had this situation as on the picture, so we had only pure cornerstones, and the difference in concentration of cerium, if it led only to different proportions between the pure cornerstones and the material, the spectra would not change, because the atoms in one cornerstone, you don't see the atoms in another one because it's just far away. So in EXAFS, you don't see contribution of another cornerstone when you measure in the EXAFS signal of cerium or zirconium. You see only the contributions of the atoms in the same cornerstone. So if all the cornerstones are the same, either pure cerium or pure zirconium, the spectra should not change as a function of cerium content. This is not the case. They definitely do change. And that means that we have mixture of metals. We have different metals in the same cornerstones. So we can have it, and we do have it. So the first question is answered, and then the second question is more difficult. So what happens? Let's zoom in into the part that is actually a cerium-cerium or cerium-zirconium scattering. So the second peak we see here, this is the peak at around 3.5 angstroms. Here you see that the dependence of the intensity and position of this maximum, so the panels A and C, if you just look at it, it can also give you a hint of what happens. It appears, and you will see later why it appears so, that this dependence of the data can be explained by a coexistence of only three different types of cornerstones. Mainly, of course, there can be some minority fractions of virtually anything, but mainly there can be three main ones. So pure zirconium 6, pure cerium 6, and cerium zirconium 5, the mixed metal ones. And the evolution of the concentrations of the weights of this cornerstone can be as follows. So you can mainly have, as a dominant fraction that forms predominantly, you can have cerium zirconium 5. And then, to respect the stoichiometry of the whole compound, the rest of cerium or the rest of zirconium can go into either pure zirconium at lower cerium content or pure cerium cornerstones. So the concentration profiles are as follows. What would it give us? So at cerium KH, example. Serum, so with the increase of serum content, the peak would shift to the higher R, because you have more and more contribution of serum scattering, which, and distance between serum is higher than distance between serum and zirconium. It will also get broader at the intermediate concentrations, because you will have roughly the same contribution from serum, and serum zirconium. And it will also get less intense, because this contribution will most probably be out of phase with each other, so the intensity will go down. And so you should have higher intensity for low serum content and for very high serum content, and that's what happens at zirconium KH. This hypothesis that we have, this qualitative hypothesis, would imply that we should have high intensity and basically high intensity of the main maximum at lower concentrations of serum, because the fraction of pure zirconium 6 octahedral would be the highest. So it would be the pure zirconium, and then with some small contribution of serum zirconium scattering. But then starting from, to be precise, like 17%, so 1/6, when all the serum, when you have no zirconium 6 anymore, but you have only serum zirconium 5 and serum 6, starting from this point, the spectra should stop changing, right? Because what will change from 17% is the ratio between the serum zirconium 5 and serum 6. But for each particular zirconium atom, the situation does not change at all. So all the spectra should be very, very similar. Of course, there can be some small differences between them because of some minority phases. But in principle, the spectra should not change much. And that is exactly what we see here. You see that we have the highest intensity of pure zirconium that is lower for serum 10, is even lower for zirconium 22, but then between serum 22, serum 45, and serum 84, it does not change that much. So the changes are very, very small. So at two edges, this confirms qualitatively yet our hypothesis of the coexistence of just these three main phases. The good point about EXAFS is that we can do fitting, and we can confirm this hypothesis even quantitatively. So what we did was a fitting at two different edges of 10 different spectra as this single data set. So we fitted a single data set containing 10 different spectra that resulted into a production of like a single R factor, single figurative merit, and that allowed us to fight the correlations, because in different data sets we assume that the distance between the serum and zirconium, so at serum KH, when we fit serum zirconium distance, logically should be the same at the distance between zirconium and serum at zirconium KH. So we have the same path, basically the same thing, in the two different data sets and at two different ages. So like this, we don't have the factor of 10 as a number of parameters. We have the number of parameters grows much slower than the number of data sets, the amount of data. And the same is true for the Debye-Waller factors. So this allowed us to fit the whole thing without having too much problem with correlations. And the data fitted quite nicely, so the result is good. The global R factor is low, but also each individual R factor for each particular fit under these constraints is also good. And that confirms this hypothesis of the preferential formation of serum zirconium-5 and the formation of complementary phases of zirconium-6 and cerium-6. So this is, I think, quite an instructive example of multiple edge EXAFS fitting. Another example is UIO67 metal organic framework functionalized with a linker functionalized by different molecules. The thing is that the pure UIO67 MOF, yeah, UIO67, this is UIO67, the previous one was UIO66. So UIO67 contains biphenyl linkers, which can be exchanged with bipyridine. Some of them can be exchanged with bipyridine, and bipyridine can be functionalized by something. So these two nitrogens can host metal, and this metal can be used as an active site for chemical reactions, for catalytic reactions. They can be these MOFs can be synthesized and functionalized in different ways. You can do one-pot synthesis, you can do post-synthesis functionalization, but the result is should be the same in principle. And this is a MOF with 5 to 10% linkers of which are exchanged from biphenyl to bipyridine, functionalized with metal. In our case, it was platinum. Fitting the MOF, the question was whether the linker is not damaged during after the functionalization. So whether we have the same environment of platinum in the MOF as a part of this linker, functionalized linker, as we have in a separate linker molecule. So whether we damage the linker during the functionalization when it's inserted into the MOF. And the answer is no, it's okay. So the linker is not damaged, the platinum keeps the same environment. So in order to ensure this, we fit the linker molecule, the spectrum, we measure a spectrum of linker molecule. We know, because we have a single crystal diffraction data, we know that the coordination numbers of nitrogen and chlorines are equal to 2. We fit this data, fixing this coordination number and getting S0 squared. Then we fit the spectrum of the MOF by fixing the S0 squared to the one we obtained for the linker. And we get coordination numbers of roughly 2 for chlorine and nitrogen. And of course, we got also the bond distances. And since the coordination numbers are equal to 2 that we obtained for the MOF, it means that the platinum does not detach from the linker. So it's still there. Here, the instructive point is the unusual behavior of EXAFS signal. Look here, usually we are used to the fact that it decays with K. But here at the panel C, you see it, that for quite a large K range from say K8 to K18, the amplitude is constant, it does not change. Why? And it's actually not the worst case because it doesn't change, but at least you see it. But sometimes it can happen that the amplitude goes to 0, so you have basically a straight line, and then you start seeing the oscillations again at higher K after this straight line region. And this is quite dangerous because when you measure it experimentally, when you see the straight line just with the noise, you say like, okay, so that's it, I have to stop here. Why should I measure further? And you can miss the part where the oscillations reappear. It's quite rare, but it happens. It can happen. And the reason for this is the interplay between the two different paths, the main paths of this signal, because it's basically platinum nitrogen and platinum chlorine that have different phase. And it so happens that when the amplitude is high, so each of these signals, it's nicely decaying periodic function. But at low k, when each of these signals is quite intense, they are in antiphase, so they have a destructive interference. And at high k, the amplitude of each of the signal is lower, but they are in constructive interference, so they amplify each other. And the sum of them, of these two periodic signals, well, basically its amplitude almost does not change, and that's what causes this effect. And then another point here is that you have the overlapping contribution of chlorine and nitrogen in R, you see in the panel B. So you cannot fit separately these two paths. They have to be fitted together to get a meaningful result. And then what's interesting is what happens when we start the heat to heat the material. When heat, it's clear that both platinum nitrogen and platinum chlorine contributions go down. So we start removing chlorine ligands and we start removing platinum from the linker. Here on the left, you have a pure linker. In the center, it's MOF synthesized with platinum 2. On the right, the MOF synthesized with platinum 4, where we're supposed to have 4 chlorines instead of 2. So the question is here, is there an interval of temperature where we remove the chlorine from platinum, but do not remove platinum from the linker? So we break platinum chlorine bonds, but we don't break platinum nitrogen bonds. In order to answer the question, we can fit the whole sequence of the spectra measured during the temperature ramp. So we keep the interatomic distances and S0 squared fixed, and we look at the Debye-Wohlers and coordination numbers, because the coordination numbers, that's what tell us whether platinum stays with their chlorines, whether it stays coordinated to the linker molecule or not. And here you see the result of the fitting. In bluish, you see the coordination number, and in reddish, well, the pink and the orange, you see the Debye-Wohlers for 2 different shells. And you see that until like 500, well, almost like 600K, things go well. And then after 600K, things go terribly wrong, because the coordination numbers become negative. Nitrogen coordination number increases, so somehow we start having more nitrogens around platinum. Instead of 2, we can have 3.5. The Debye-Wohler factors go negative as well, and since it's a squared thing, so it's a sigma squared. When you have it negative, it's already something that is not very physical. So that means that, of course, all those things, they do not happen in reality. We don't have more nitrogens. We don't have a negative sigma squared. In reality, what happens is our fit becomes unstable. So we lose the physical meaning, and that's another criterion. Apart from R factor, the important criterion of the goodness of an XAS fit is the physical meaning, whether it makes sense actually. And here it definitely does not make sense. So we should do something more sophisticated. And the more sophisticated thing was fitting the data in different stages. So first, the coordination numbers were fixed to 2 for NCl and nitrogen fixed to 2, and the data were fitted only in the low temperature range, so below 500K. And the Debye-Wohler factors were parameterized using the Einstein model. So we got this dependence from the Einstein formula for the Debye-Wohler factors, and the things that were actually fitted, it was the so-called Einstein temperature. So the whole dependence of the Debye-Wohler factor is determined by the Einstein temperature and well, the temperature of the sample. And fitting the data in this range, we obtain these Einstein temperatures and E0, okay, at low temperature. Then we used the same Einstein temperatures for chlorine and nitrogen to calculate the Debye-Waller factors also at high temperatures. So we extrapolated to a high temperature, supposing that it should be the same. The Einstein temperature should be the same. And then we fixed the resultant Debye-Waller factors and fitted only the coordination number and E0. It's probably easier to ask questions in the question and answers because other people cannot follow them. It's better to use this rather than the chat, just as a comment. But it's okay, it's just for convenience. Okay, so using this strategy, we can feed the data, the sequences of the data, and we see now that it starts making much more sense. And we see that indeed there is some interval between 600 and 660K, where most of platinum chlorine bonds break and platinum nitrogen stay almost intact. Here you see that the dependence on coordination numbers is pretty reasonable. For a platinum 4 MOF, you can see that already in the beginning, we start losing quite a lot of, we lost already quite a lot of chlorine. So you don't start with 4 of them, but you start with roughly 2.5. And then an instructive picture is here. What happens when you substitute the chlorine ligands with something else, for example, with bromine, or with this molecule, methyl. We see that what XAS gives us is information that the molecules, the platinum functionalized with these molecules, it's still attached to the framework. So always the spectrum contains a contribution of 2 nitrogens because the fits in coordination numbers of nitrogen and the fits that are quite good. The coordination numbers are 2. And you can also see an effect of substituting chlorine with bromine. So the intensity increases a lot, the signal changes completely. So that's it illustrates the chemical sensitivity of XAPS. So the bottom line, when to think about XAS. So you need to think about this method when you need element selective information about your sample. When you need information local in bold, local geometry and electronic structure. It can be also useful when the sample is not crystalline or not solid. So other more, let's say, robust and widely used methods like X-ray diffraction, they don't work. So if it's amorphous thing, you cannot get much from diffraction if it's a liquid. So you might be interested in using XAS, but of course XAS is also perfectly applicable to crystalline materials as well. So it's not an issue for XAS, but it can be an issue for other techniques. Sometimes the species of interest that you look at can be disordered inside the matrix, in porous matrix, like I don't know, like a metal ions inside the zeolites or metal ions inside the MOF. So the whole thing is crystalline and nice, but the active sites, those that you are most interested in, they can be disordered and they can be very few. So you would not see them at all in diffraction, for example. So in this case, XAS can be very helpful because you can look only at this species, exploiting the element selectivity of the technique. Yeah, then you can have a species of interest too small to diffract when you have 1 nanometer nanoparticles or 2 nanometer nanoparticles. Also, diffraction can be quite difficult, but for XAS it works fine. And then, well, it's a common thing for most of hard X-ray techniques when you need the in situ operando measurements, because the hard X-ray techniques are well suited for operando application because of the high penetration depth of the X-rays. Then, of course, you should use as many relevant methods as you can to characterize your system in And since XAS is mostly used in synchrotrons, where it's not very easy to get beam time, it's better that it's not the first technique that you use to characterize your samples. You'd rather come to a synchrotron to do XAS with a well-defined questions based on the prior knowledge that you have on your sample. So a couple of words about XAS experiment, how it works. Well, we have a source of the X-rays, bending magnet or wiggler on undulator. Then you remember that we studied the dependence of absorption coefficient on energy. So we need something to tune the energy, to define the energy and change the energy, scan the energy. So usually what is used for this purpose is a monochromator. That is basically a couple of crystals, of single crystals of silicon, usually silicon 111 or 311, 511. But there are other cuts that can be used. And the working principle of this device is based on the Bragg's law. So you, when you place the crystal at a particular angle with respect to the incident beam, only those photons, whose energy or wavelengths satisfy the Bragg equation here, only they get reflected. So like this, by changing the angle of the monochromator of these two crystals as a whole, so the crystal should remain parallel most of the time, in most of the cases. When you change their angle with respect to the beam, you change the energy of the reflected beam. And like this, the energy scanning is done. I say most of the time because they should remain, crystals should remain parallel most of the time, because in some cases, if you don't have mirrors, you might want the crystals to be a little bit detuned to suppress higher harmonics. If you do have crystals, you can, if you do have mirrors, you can keep the crystals parallel all the time. And that's what you want to do usually, because you don't lose intensity there. So the mirrors help you to reject higher harmonics coming from the source, and also possibly to do the focusing of your beam. If you want to go to the micro beam or nano beam, you have to do it with the mirrors. Then you have your sample and your detection system. In the most classical way, the detection is basically 3 ionization chambers: I0, I1, and I2. And I2 is needed to measure also a reference sample together with your actual sample. Reference sample is usually foil or some other standard material, which is measured together with your actual sample all the time. So with each sample, each spectrum of your sample, you get a spectrum of reference. This is needed to discriminate between the actual changes in your sample because of some chemistry, some chemical treatment or heating or whatever, and the drift, for example, drift of the energy of the monochromator. Because you remember we had an edge shift, chemicals, you can have a chemical shift due to the change of oxidation state. So this is a physical chemical process. But there can be also a shift just because the monochromator is a little bit tired, and it drifts a little bit with time when you do multiple scans, temperature changes, temperature in the experimental height changes, and or some parts of the micrometer get heated, so the energy can drift. So in the former case, with really a physical thing happening with your sample, the spectrum of the reference sample should stay same. On the contrary, when it's a monochromator thing, so it's experimental error, let's say, the reference spectrum should drift as well. So we can use the reference spectrum to align the spectra of the samples, because the reference spectrum should stay always at the same energy, because nothing happens with reference sample. There is no chemical treatment, there is no heating, there is nothing. So we can use the reference spectra to align the actual spectra of the sample. And this is a feature that is realized in Athena very nice in the software for data analysis. You can use it there. Then the detectors I0, I1, and I2, they are usually ionization chambers. This is basically the volume filled with gas that is ionized when the X-ray photons pass through it, and you measure the current that is created because of this ionization. Another way to measure the spectra is the so-called fluorescence mode, because when you absorb the X-ray photon, you create a core hole, right? You eject an electron and create a core hole. The core hole is filled by a transition from higher orbitals to this core hole. This transition is accompanied by a fluorescence of the X-ray photon. So emission, you have basically you see an emission line. And the more photons you absorb, the more holes you create, the more emission photons you have. And so the higher the fluorescence yield. So the fluorescence yield is proportional to absorption, to how much photons you absorb. So you can get an absorption coefficient from the fluorescence, just dividing the fluorescence intensity by the I0. Here it's without a logarithm. So you have basically two main ways, if you don't take electron yield, it is a little bit more exotic for hard X-rays. You have two main ways to measure the spectrum: transmission and fluorescence. So which one to choose? Basically, transmission is used, fluorescence is used when your sample is either too dilute, so the total absorption, when the edge jump is too dilute, it means that there is very few of your absorbing species. In the edge step, the height of this edge jump you see on the left, the delta mu, is very small. So the signal is very small, the oscillations are very weak, and the noise, it's always the same. So the signal to noise ratio is low. So you may get better results using fluorescence. So indicatively, when the edge jump is lower than 0.05, you should consider at least testing the fluorescence, see whether it gives you better results. The second common case when you use fluorescence is when your sample is too absorbent, so nothing passes through, nothing or very little passes through. It can be, for example, when you measure, I don't know, a coating on a slab of, I don't know, steel, coating on a steel support, thick steel support, thin layer of coating, you have nothing in transmission, so you have to measure in fluorescence. And for all the rest of the sample, so when the edge jump is higher than 0.05 and the total absorption is lower than 2.5, you'd rather measure transmissions. That's what I call reasonably good sample. So you should privilege transmission because the measurements in transmission are faster. They have better signal to noise ratio, and usually they have less distortions due to the self-absorption or the things. So it's better always, if you can, measure transmission. Then if you cannot, it's better to have fluorescence than nothing. But you should privilege transmission. So very important thing before XAS experiment, or even before considering XAS experiment, you already have an idea that might be useful, but you are not really sure that it's feasible. It's better to optimize the mass of your sample in order to get an idea of how good can the quality of your data be. And if it can be reasonably good, how much sample you should put in how much material you should put in your sample to do a good measurement, how much sample you should synthesize. This is very important, and this can be done with a software, very nice software that is called XAS Mass from Konstantin Klementiev and Roman Chernikov, who are now in Max 4 and in CLS. So basically, This software asks you for a chemical formula of your sample, just a molar formula. And based on this molar formula, you can calculate how much sample you need and how high the edge jump is going to be. So you insert the chemical formula, you set the total absorption to something around 2.5, between 2 and 2.5. So how much your sample you wanted to absorb in total. Then if you do a pellet out of your powder, you give the diameter of the pellet, the area of your pellet, sorry. You set the energy of the edge that you want to measure. If you don't pelletize your samples, so the samples don't have a well-defined area, you set the bulk density, because in such case, the information that you will get will not be the mass of the sample to measure, like in case of the pellet, but it will be the thickness of the sample that you will have to create to get a particular edge jump. So, and then when you inserted all these values, you will either get an optimal mass in case of pellet or optimal thickness in case of, for example, capillary filled with powder. And if your resulting edge jump is too high, so the sample is too concentrated, you should decrease the total absorption until the edge jump goes below 1.5. So, and this will give you an idea of whether the measurement is actually feasible. So if the edge jump is high enough to do a measurement in transmission, for example. Whether the edge jump is too high or not. So whether you should dilute your sample or not, because if the edge jump is too high for a pellet of reasonable thickness, then you should dilute, because let's say if the optimal mass is too low to make a good pellet. So if you have, for example, the results that you need a 10 milligram of powder for a 13 millimeter pellet, you will never be able to do a 13 millimeter pellet with a 10 milligram of powder. You will need something like 30 milligram at least, or better 60. But if you do a pellet with 60 milligram of such powder, you will absorb everything, and the measurements will be bad. So you will need to use something to dilute the sample, like cellulose or boron nitride or diamond powder, something like this. So you'll get an idea whether you need to use these techniques or not for your experiment. So this is very, very important, this test. It has to be done before every experiment in order to understand how to conduct experiment, which data quality to expect, and in which mode to measure, and how much sample to use to prepare, how much material to use to prepare your sample. So this is like super important for XAS experiments, so highly, highly recommended. Some tips to do a good measurement. Well, you should optimize, as I said, the mass and thickness of the sample well before the experiment. You should prepare as homogeneous sample as possible to check with vertical and horizontal scans whether it's really homogeneous, because the thing is that we measure X-ray absorption at a particular point of the sample, right? If your beam moves during the measurement, which happens, fortunately, it can happen because the monochromator is tired, or because there is a glitch and there intrinsically the beam moves a little bit. But if the beam moves, you start measuring for a while, for some points, you start measuring and at a physically different point on the sample. And if this, in this different point, the sample absorbs more or less than in your usual point where you measured before it, then you'll have a dip or a peak in your absorption spectrum. But this dip or peak, it will not, or step, it will not be because of the
increase of the absorption coefficient of your sample. So it's not going to be like a chemical effect. It will be just because you're measuring on a thicker or thinner, or let's say more or less concentrated part of your sample. And you can fight this only by doing the sample as homogeneous as possible. And when you do a vertical or horizontal scan, just scan the motor of your sample stage, you can see it very well. So you can assess the homogeneity of your sample, and you can move to a point that is the most homogeneous. So this is very important to do. So, and also there is another consequence, is that when you're doing in situ measurement with some process that may cause the shift of the sample, then you should do your best to avoid it. So it can be, for example, when you heat the sample in a cell, the cell may expand. So because of the thermal expansion, the cell can move when the temperature of the sample changes. And so if your sample is not homogeneous, you will see artifacts and distortions in your data, or in the best case, you'll just see increased noise when the cell moves. So at different temperatures, you come to a different spot on the sample, which may be not very good spot. So it has to be avoided. Another common problem is that when you measure capillaries and you heat the sample, and the capillary is not quartz, but is glass, and if you heat it too much, the glass will become soft, and the capillary will bend just because of the gravity, and it can go completely out of the beam, or at least it can move a little bit, which for capillaries is even more drastic than for pellets, because in the capillaries, the sample is intrinsically dishomogeneous. First of all, because the cross-section is round, it's circular, and because it's a loose powder. So in capillary, it's loose powder, so there are holes, there are voids anyway. So when you do experiments with heating, be careful and be sure that your cell does not move. And if it moves, try to compensate for it. There are ways to do so. You can use a feedback with move. You can move, for example, the table with the cell as a function of temperature. So if the beamline has the possibility to do so, you can move the position of the cell in vertical as a function of temperature to compensate for this expansion, or you can use quartz capillaries instead of glass capillaries when you want to go to higher temperature, and so on. Then, yeah, okay, the sample has to be homogeneous. So please do not measure powder samples on tape, because sometimes there is a technique from good old days to put powder on a Scotch tape, just to use powder on a Scotch tape, and like this several layers, and then you measure. So like this is not a good way to do. If you measure pellet, if you measure powder, it's better to measure it as a pellet of optimized mass, not as a powder on tape. Then, yeah, again, another source of movement of the beam on the sample is the vibrations. So check that the sample stage is not vibrating. If you have a pump or cryojet or something that shakes your sample, it will most certainly kill the quality of your data. Another thing that is much less evident, much more subtle, is that, well, the main goal here is to eliminate things that can change the absorption coefficient of your sample. That is not the actual changes in the chemistry of your sample, right? And the sample in XAS terms, let's say the sample is everything that is between the two ionization chambers. So it's your actual pellet or capillary, but also the air, also like everything else. Yeah, mostly the air, the windows. And so apart from the obvious things that your table should not vibrate, so you don't measure in different points of your actual pellets, you should also ensure that the other conditions, what is around your pellet, also stay stable. And what can be not stable is actually the jets, or let's say the flow of warm air that can be around your sample. So if there is a turbulent flow, if you heat your cell
the air around it, gets warm. Warm air, hot air, it absorbs less than cold air. And if then you have an air conditioner that switches on and off and creates a flow of air once in a while around your cell, that you can have sometimes very warm air around the cell, sometimes very cold air, well, relatively cold air. Difference can be hundreds of degrees if you heat to, I don't know, 500 K or 500 Celsius. And this difference, you can see it in your XAS data as noise. So we were very surprised when we saw it actually, because you would say that it's not much, the air does not absorb much. But in EXAFS, you are sensitive to the changes down to 10 to the minus 4 as of the X-ray absorption coefficient. And these changes can be very well introduced by this kind of effects. So now for some cells that are warm, we use a jet of cool air, not to cool the cell, but to create a laminar flow of air of the same temperature around the cell to compensate for this effect, to be sure that the absorption of air around the cell is constant. And these effects, they are, you can see them even at relatively high energy. So we saw it at 10 keV, 9 keV for copper. So at high temperature kills your EXAFS completely. When you install a jet of laminar flow around the cell, data become much better. So when you use high temperature cells, pay attention to this. Check whether the edge jump is what you expect from the calculations, because if it's not, maybe the synthesis went wrong and the actual amount of the material of the absorbing species in your sample is different from what you think it is. Then maybe you should redo the sample to get a better measurement. Yeah, then of course use reference foil or reference samples to align the data. So you remember this second sample in between I1 and I2 ionization chambers. Always use this when you can, when you measure transmission. Use this because it can be very useful, even if you think, or your beamline scientist thinks that the beamline is super stable, the beam does not move, the monochromator doesn't drift, sorry, the energy does not change. It's better to be safe than sorry. It's better to use a reference foil always. And also a rule of thumb, it's better to have a little of data than a lot of bad data. So if something, you think something is fishy about your experiment, sometimes this little detail and then ruins the data, and or at least make very difficult the data analysis. So if something seems fishy, it's better to investigate, spend some time on it. So, and then the final part is some very short overview XAS facilities at the ESRF. So XAS is a very popular technique here. I have a lot of beamlines that do XAS with different flavors. You can have, so the large group of beamlines are so-called CRG beamlines, collaborative research groups that are run by scientific committees of different countries. And most of these beamlines, they do XAS in one way or the other. So we have the Italian beamline, German beamline, French beamline, Swiss Norwegian beamlines, British beamlines, and so on. Most of them do XAS. And then also among the ESRF beamlines, there is BM23 and ID24. That's where I work. So general BM23 general purpose EXAFS beamline. ID24 is undulator based high brilliance XAS beamline. There is a now dispersive branch, scanning branch, but there are also a set of undulator beamlines, undulator ESRF beamlines for XAS with different flavors. Let's say ID32, the soft X-ray spectroscopy beamlines, ID26, where the XAS is coupled with the XES X-ray emission, ID12 for the polarization dependent XAS, ID21 the microbeam, XAS with microbeam, ID16B nano beam, and so on. So all of these beamlines, they have different characteristics. You can check them at ESRF website.
We're going to talk a little bit about BM23 ID24 because, well, I work there, so I know these beamlines better than others. Here, the main activities are divided into two large parts. Chemistry, so we do a lot of catalysis, electrochemistry, solution chemistry, and so on. The conditions can be quite mild there, so this is, let's say, catalytically relevant temperatures, industrially relevant temperatures, let's say below 1000 degrees, something like this, and relatively low pressures. We have a possibility to control the gas atmosphere, to change the temperature, to use a lot of complementary techniques, infrared, diffraction, XAS, mass spectrometry. And there is another part that is dedicated to extreme conditions. So mainly it is physics, and it is the studies of matter under very high pressures, very high temperatures. So have pressures going down to hundreds of GPa, temperatures going up to thousands of Kelvin, magnetic fields going to tens of Tesla. So here it's different applications, different instrumentation. You have laser shocks, diamond anvil cells, and large volume presses to study matter at these conditions. So I'm responsible for chemistry part. So I just show a couple of slides about our chemistry activities. They are mostly at BM23, so general purpose XAS beamline. We have excellent stability of the beam there, wide energy range, possibility, okay, not the obligation, but the possibility to focus the beam down to several microns. Most often for chemistry, we don't focus because the samples are large, and focused beam for chemically sensitive samples, it can influence the chemistry that is going on. So you have some radiation-induced effects. And another beamline where we'll do some chemistry is ID24 DCM with a double crystal monochromator designed in ESRF that will be installed actually in the next months. This is a completely new beamline. It is built on the place of one of the hatches of old ID24, the energy dispersive ID24 that had two branches. Now only one branch will be kept energy dispersive for very fast experiments where you need to measure very fast with laser shocks with pulse magnetic fields. But the other branch will be converted into a scanning beamline, so the DCM with double crystal monochromator. There it will be the same undulator source, so there'll be a lot of photons, possibility to focus the beam down to 1 micron, or it's again not an obligation, so we can use a large beam as well. But the goal is to collect the good EXAFS data time down to 1 second. And it's possible, of course, to measure even faster. In principle, now the technology allows to do this. But here the thing is that we'll have a lot. When you measure very fast, you can have a bottleneck, just the number of photons. The statistics can be bottleneck. But here we hope not to have this bottleneck and to measure, to have a good analyzable data already in 1 second. Yeah, so the BM23 will be used for slow chemistry, relatively slow chemistry, C2, operando, industrial experiments, and the ID24 DCM will be dedicated to faster chemistry where you need to really measure fast, or to space resolved experiments where you need to measure fast at many different points in the sample. So we are very well equipped. Chemistry, we have a lot of equipment for gases. We have a lot of different cells. We have different complementary techniques like diffraction, like mass spectrometry. We can do UV spectroscopy as well. One of the highlights of BM23 and ID24 is combined infrared and XAS setup. So we have a dedicated cell developed by my predecessors, Giovanni Agostini and Mark Newton. And this cell can be used in to to measure together XAS and drifts. So now we modified quite a lot the optical scheme of the setup. Here you cannot see it because it's inside this box. The box is needed to remove CO2 from the optical path, the CO2 that is in air, and it contributes a lot to the infrared spectrum. And yeah, that's why it's a greenhouse gas, right? Because it absorbs a lot of infrared. But there we have a drifts detector, some mirrors, infrared mirrors to collect together the infrared data and the XAS data. And it works very, very nicely. So we have nice examples coming out. So this one made our ICS Catal a couple of years ago. This was a nice study of platinum hydrides carried out by a team from Turin University. Very, very nice. At the same time, we saw the modification of the platinum, the structure of platinum nanoparticles, and the modification of the hydrides, platinum hydrides that were created on the surface of these particles upon exposure to hydrogen. And all this was as a function of hydrogen partial pressure that we monitored, also the amount of hydrogen in the feed we monitored also by a mass spectrometer, all measured at the same time with the same sample, which is particularly important for this kind of experiments. Because if you do them separately, then you might, in different cells, you may start having questions of whether the conditions are actually the same for different experiments. Here it was all done in the same cell with the same sample with the same setup, which is very, very nice. So if you need to combine the drifts and XAS, so BM23 and ID24 may be a nice option. Then another novelty is that in ESRF now we have, after the shutdown, after the advent of the new EBS source, we also have not only a new source, but also a new control software. Now it's called Bliss, and it's fully based on Python. That means that it's much easier to write your own macros because not so many people outside synchrotrons knew what spec was, but quite a lot of people know what Python is. So your macros can be written in Python, and it makes it much more friendlier to users and gives a lot of possibilities. So we have it in BM23 and ID24, we have the macros to control remotely, to control gases, valves, to control temperature. So basically now, everything can be done, can be automated, can be done remotely, or can be put into macros if you have, for example, a chemical treatment to do, which consists of different temperature ramps, different changes of different gases. It can be all put into a macro, and you can you don't have to like physically come into Edge, push the button, or stay behind the laptop to push the button to change the gas flow when it's time. No, you can program it, and the beamline will do it for you, and it's going to be fine. And in some rare cases, when it's not fine, well, you can receive a notification on your smartphone saying that there is something wrong. The temperature is not as you expect. The flow is different from what you expect. Maybe you forgot to open the gas bottle, or something else happened. Or maybe everything's fine and your macro has ended successfully. So you can start doing something else, something new. So you can get an email, you can get a Telegram message. And yeah, all this has been working pretty well, and that allows us and our users to produce some pretty nice publications. So we will be happy to count you among our new users in the future if you think that XAS can be useful for your research problem. And with this, I thank you for your attention. I thank also all these very nice companies that helped us to organize the user meeting, our dear sponsors. And now I'm ready to try to answer your questions. And in case you'll come up with some other questions later, please do not hesitate to write me an email.
ask. I will just put a screen with. I will put a screen with my email so you can remember it. Yeah, I hope now you see the title slides. Yeah, and my email on the bottom. So please feel free to drop me a line. And yeah, now we come to the questions. Okay. First one is from Fyodor Shahov. He asked, what is the sensitivity of the methods if the sample is a mixture of different materials and we have to study the minor one? It's always difficult. And of course, here the universal answer, it depends on the sample. You can probably, well, then it depends. I mean, globally, it depends whether your mixture is of the species that contains the same absorbing atom or not. So if your sample, for example, imagine you have, I don't know, huge iron nanoparticles that are not actually nano, they are iron particles. And you have the surface species that are redox active and that do the job in your catalysis, and you have the bulk species that they don't do anything. Basically, they stay the same. And you measure the spectrum, and in the spectrum you'll have an average between the surface species and the bulk species. But since the bulk species are 99% of your iron, they will contribute as a 99% of the intensity of your data, and the remaining 1%, only 1% will be of your surface species that you're interested in. In such case, you have a big problem. So you'll have to do maybe difference spectra or do some tricks to avoid this. But in such case, it's pretty hard to do something if your species of interest is less than, I don't know, 5 or 10% of your absorbing species. But then if your minor species are not of the same, if you're interested in the minority species, but the majority species do not contain the elements that you want to study, then you can go down to ppm. So you can measure, that's what's done very often in environmental science, because when people measure soil, for example, they are interested in, I don't know, some traces of whatever lead in the soil. You don't have the percents of lead, you have their tens of ppms, or it can sometimes go even lower. There, of course, you'll have to measure for a long time, but you can get data, reasonable data, even at the ppm range. Like rare earth metals and carbon. Yeah, there it's fine, because rare earth metals, they are different from carbon, right? So they have the only thing that you will get in your data will be the signal from your good absorbing species that you're interested in. And there, yeah, you can go down to, depending on how fast you want to measure, you can go way below percents. You can go to, if it's a several percent, then you will be able to measure the spectra very fast in matter of, in transmission mode, in a matter of seconds or tens of seconds, or even less. If you go down to ppm, if you're looking for some traces, if you're going down to ppms, then of course you will have to measure them in hours, and the quality will be worse, but you will still be able to get the data. Then Julian asks, can you quantify the correlation coefficients on the fly between different fitting parameters to check if you can trust the parameters? Yes, usually the common software that is used for this, like Larch or Demeter, they give you the correlations. They give you the value for the correlations. So if you see if your correlations is, I don't know, 0.99, then you're in trouble. If it's below like 0.9, then it's still okay. And also the indirect indirect measure of strength of the correlation is the errors that the software gives you for the structural parameters. If you see that your E0 is 1 plus minus 20, that means that it's also most probably due to the correlations and the fit is not very stable. Or if the Debye-Waller factor is 0.003 plus minus 0.1, then it also means that there's something to be done to improve the fit. Then Steen asks whether it's, yeah, okay, similar question, but for light elements like lithium, whether absorption would stem from heavier atoms like oxygen transition metals. Okay, for lithium, okay, this is a big problem that one can face for XAS experiments. Well, okay, speaking about lithium, it's not hard X-rays because lithium K and KH will be like super low. We cannot reach it in ESRF, and you can probably, yeah, what's lithium? Let me see. Yeah, it's what, like 30 electron volts or something like this. Yeah, this is super low, so it's not reachable at all. But in general, your data quality, your life is much harder when you want to measure something light in the matrix of something heavy than vice versa. So if you have, if you measure, for example, I don't know, a titanium zirconium alloy, and you measure titanium, you have 1% of titanium on zirconia, something like this. Then, of course, your total absorption will be very high because zirconium absorbs a lot at 5 kiloelectron volts, where there is a titanium edge. And the data quality will be pretty low. It's much better to measure 1% of zirconium on titania than 1% of titanium on zirconia. But it is doable. And for this, actually, you need to estimate the edge jump in XAFS mass, you see, because like this, you can already get an idea about the data quality. Because if you see that, for example, your edge jump is 0.03, that you will already know that most probably you'll have to measure in fluorescence. And you will need to plan to, I don't know, something like 1 hour per spectrum, and you can adjust your experimental program accordingly. So it's a general answer. So it's harder to be more precise, but the general rule is like this. So Roman Werner asks, what are the different assets of L and K edges for 3D metals? So the difference between different edges is where the excitation comes. So where is the core hole and what empty states are filled. So what orbitals you probe, what empty orbitals you probe. So in case of K edges, you probe mostly P states, P states. It's 1s to P. And in case of D, you probe S. In case of L edges, you start from P orbital and you probe S and D. So for 3D metals, when you do L edge spectroscopy, you have direct access to the holes in D band. And since this holes, this orbitals is the D shell is being filled in 3D metals, right? And there's a number of empty space there determines the oxidation state, for example, chemical properties of the metals, and this L-edge spectroscopy on 3D metals can be very powerful of this, to see this. The problem there is that to do L-edges of 3D metals, you have to go to soft X-ray beamlines because energies are pretty low. When you go to soft X-ray beamlines, the problem is that it's hard to do in situ and operando measurements because it is possible. So I know that at the Letra in Trieste they can do this, but it's a very difficult because you need to have a very specialized cells, because the whole idea is that when you do soft X-rays, you need to be in ultra high vacuum because otherwise you'll absorb everything. All your X-rays will be absorbed in your gas. And if you want to do in situ and operando, you want to interact, for example, with gases, and it's hard to interact with gases in ultra high vacuum. So then you have to do some tricks to do this. So, but at the KH of 3D metals, you don't have this problem because the energy of the X-rays is way higher. You can shoot through the gases, it's not a problem. You don't have direct access to 3D orbitals, but you can have it through the pre-edge. You remember the different pre-edge intensity, or you can see the difference in symmetry or oxidation state with different pre-edge. So it's complementary, but for in situ operando measurements, K edges are more preferable. Also at K edges, you can do EXAFS. At L edges of 3D metals, since it's soft X-rays, it's pretty hard. There, it's much less meaningful. But for studies of really precise study of electronic structure, L edges of 3D metals can be useful. Anonymous attendee asks whether there are any concerns with regard to radiation damage and oxidation state being changed due to primarily a secondary radiation damage mechanism. Yes, yeah, of course. The answer is, of course, yes. We can have radiation damage when you physically like a burn hole in your sample, or we can have radiation-induced effects when under the beam, for example, the chemistry that is being done by your sample is not the same as it is when there is no beam. This is a very common problem, common issue, and there are different ways to tackle it. So the first step is to understand whether it is the case for your sample. So you can measure very fast, try to measure as fast as possible, several times, to see whether the spectrums that you get are identical. So whether your spectrum does not change when you measure, I don't know, 20 spectra, one after the other, if the first spectrum is the same as the 20th. If it is the same, it may mean two things. So either you don't have the damage, or it's very slow, or it's very fast and already the first sample is completely burned. The sample after the first spectrum is completely burned. You need to have some prior knowledge of the system to understand this. When you do a long chemical treatment, measuring in one spot, sometimes to check whether you are seeing radiation damage effect or not, you can move to a fresh spot on the sample to see whether the spectrum is the same as the fresh spot or not. If you see the radiation damage, you should measure faster. You should attenuate the beam, probably. And then if you attenuate the beam, then you will lose in the data quality, of course, because you'll have less photons, but maybe the data quality will still be sufficient to solve your scientific problem, to answer a scientific question. If your sample allows it, you can use a cryostat. So this is a very common way to tackle radiation damage because it appears that at low temperature in the cryostat, the radiation damage effects are smaller. So if you are measuring something ex situ, you may want to cool it, and radiation damage will be less of importance. You can measure, if your samples are homogeneous, you can measure a different spot of the sample every time. And for example, some beamlines have these macros routinely implemented, like at ID26. They have a lot of photons. They sometimes have to do long acquisitions, like X-ray emission spectra. They take a long time. And so they measure, one of the ways to tackle the radiation damage is to measure the new spot, the new point, each point of the spectrum, to measure it on a fresh spot on the sample. Like this, you can have you can acquire for 1 hour on the samples. They can leave only, I don't know, 1 second under the beam. You just need to have a large enough sample. So it's a very important question, and it's a very important issue that has to be faced and has to be taken into account, because especially when your samples are fragile, like organics, something polymers, something like this, or when your chemistry may be sensitive, you do some catalysis that can be radiation sensitive. Yeah, and then of course, if you do some microbeam studies, when you focus the beam, then you will have even more of this, because it's a number of photons per unit area that matters here. So another option can be defocus the beam to do this, to decrease radiation damage, but this is of course also implies other limitations. Amrita asks, could be such 2H EXAFS fitting for compounds with light elements like carbon and boron? In principle, yes. In practice, it's pretty hard, because if your carbon and boron are the neighbors, so if you measure, I don't know, for example, copper that has carbon nearby, and you measure copper KH and I don't know, have a copper zinc alloy, and you have a carbon for some reason there also somewhere, and you have copper carbon and zinc carbon scattering, then of course you can measure it at both copper and zinc edges. But if you're talking about measuring carbon and boron edges in combination with something else, then it's difficult already, because carbon and boron, again, it's soft X-rays. It requires a completely different beamline, completely different synchrotron, most probably. So you can have the data, you can have complementary data on carbon and on whatever other thing there is in your samples that you can measure at hard X-rays. But I'm not sure that you can get a good EXAFS at carbon. You will not, and a good EXAFS at boron, not really. So you should use this data as a complementary thing to get information about your system. It's very nice, but to have a multiple H EXAFS fitting, I think it's going to be hardly possible. First of all, because EXAFS at carbon and boron is difficult, and then because the experimental conditions will be just too different to have the same common parameters in the EXAFS fitting. So usually the power of the multiple edge fitting is that when you measure the same beamline with the same everything, just two different edges, and even the same sample, so then it's really it's where it's most applicable. Then again, a question from Romain: for a given system in which we expect disproportionation over time, what is the strategy that should be used to analyze the data, since the edge region shows an average oxidation state and won't move? I'm not sure I get the question, because you have no choice but to have an average in your XAS data. So if your system undergoes changes that change the average oxidation state in general, average local and electronic structure of your absorbing species, you will see it in the data, and then it's up to you to use different decomposition techniques like linear combination fitting or PCA or MCR to disentangle this mixture to get the spectra of separate components of this mixture. If the changes that your system undergoes changes that do not lead to change of the shape and position of X-ray absorption edge, first, this is probably not very likely, because maybe there are no changes at all. So if something changes, you should in principle see it, unless there are some few exceptions, but still. But if it so happens that something changes but the spectrum does not change, well, then you cannot analyze these changes by XAS. So I'm not sure whether it answers the question, but it's maybe I misunderstood something about the question, but this is the idea.
Okay, there is a question from Huan Yu. Long question. Taking a lithium in organic solid state battery during charging process, for example, lithium ion flows from lithium metals through solid state electrolyte to the reduced cathode material. Does the mobile lithium ion make any influence on EXAFS signal of other atoms of the electrolyte? Is it possible we observe any difference between with and without lithium ion flow? Some theory about lithium ion flowing in electrolyte claims the hopping of lithium ions between lattices. Will EXAFS prove the theory? Well, so first of all, you will not measure EXAFS of lithium. It is not possible because it's just too light, the energy is too low. So you can have some chance of seeing lithium as a neighbor of something else if you have some other solids. Well, if you have heavier metals or heavier elements in your electrolyte, maybe I'm not sure whether you can see lithium ion flowing, because the problem with lithium, again, even as a neighbor, it is very light, so its scattering amplitude is very low. It's very difficult to see lithium. In this case, with or without flow, you would have very, I think, minor changes, and coupled with a very low scattering amplitude of lithium, you would see probably hardly any change in EXAFS. But it may happen so that the flow of lithium ions would change the average oxidation state of other species that are in the electrolyte. Why not? And then you would be able to see it from XANES. So I would think that here the chance for you would be not in EXAFS, but in XANES, because you are more likely to see changes in the electronic structure rather than the changes in the coordination environment. So it's the same reason why, for example, in EXAFS, we cannot see hydrogen neighbors, because it just does not scatter much. So lithium hydrogens are very light. So the chance to see lithium may be only in some very ordered matrix when you have, I don't know, like 10 or 12 lithium neighbors of another element whose age you measure. Then maybe you have a chance, but see difference between flow, no flow, I'm not sure. Another question from Young is, in case the total absorption is higher than 2.5, are both the XANES feature and the EXAFS significantly distorted? What about the energy position of the edge? So if the total absorption is, well, okay, first of all, like 2.5 is like empirical arbitrary, well, empirical number. It's not exactly like 2. If it's like 2.51, it's not like it's much worse than 2.49. So the thing is that when the absorption is very high, so like 3, 4, or 5, then the oscillations of EXAFS can be damped. So the distortions that you can have is the damping of the oscillations, and also the so this is something that you see most, and also the damping of the intensity of the first maximum in XANES, this white, so-called white line. It's so everything gets squeezed. So the spectral features they get squeezed. Whether it influences more XANES or EXAFS, probably it's more important in EXAFS, but in XANES you can also see. So yeah, it influences both. The energy position of the edge, depending how you define the edge. If you define it in the same way, like for non-distorted spectrum and distorted spectrum, you can see that maybe the maximum of the derivative will change. The position of the maximum of the derivative will change just because the shape will change a little bit, and so it will seem like a shift, which is not a shift.
So it's better to avoid this, because if you compare the spectra that are distorted and non-distorted, then you can have some effects just because of the distortion. So it's yeah, I would avoid this for both XANES and EXAFS. Probably for XANES it can be even more dramatic, because you can in EXAFS you'll have just it will be like an increase of the Debye-Waller, but if it's not too drastic. But in XANES it can change the picture quite a lot by squeezing the high intensity oscillations quite a lot. So it's better not to measure something with in transmission with absorption higher than 2.5. Another question from Madeleine. Is it more difficult to analyze XAS where there is auto-absorption? Auto-absorption. Depends what you call auto-absorption. Well, I mean, if there is some problem, it's always more difficult to analyze the data. Yes, the general answer is yes. If you're talking about the self-absorption in fluorescence measurements, then, well, yes, it's more difficult because you have to find a way to compensate for it. So yeah, if you're talking about just excess over-absorption inside the sample because the sample is too thick, well, again, yes, because then you have to find a way to compensate for it. So it's better to avoid this, or to at least you have to be aware of this in order not to make in order not to confuse it with some other changes, the real physical changes with the sample. Okay, and I guess that's all. We don't have any question anymore. Do we? There is also a question from Alberto Martinelli in chat about 10% serum. For 10% serum, I see serum at apical position in the figure. Is this an experimental result? That is, it is possible to distinguish apical serum from equatorial ones. Okay, it's about the octahedra. Okay, very quickly because we are over time already. So for this morph, actually the octahedron is pretty much an octahedron. So all the positions are equivalent. So you cannot distinguish between the apical and the, yeah, okay. Because between the apical and not apical one, because they are the same. For different linkers, it may be that the symmetry gets distorted. And indeed, you can have the apical different from the equatorial ones, and then the bond distance. But what makes it different is the bond distances, right? The different bond distances. There, you can distinguish between them because the bond distances will be different. Of course, it will introduce more complexity in the fit because you will have more inequivalent sites. So it has to be dealt on a case-by-case basis. So general answer is yes, but then it will depend on the particular case. Okay. So that's it. No more questions. Thank you very much for attending. I hope it was useful. I hope to see you as future users of ESRF and hopefully BM23 ID24, or to welcome you back if you've already been here. And I want to thank our host and for the support during this webinar, and thank again for all of you for attending. So see you again next time.